Lab 2 Projectile Motion. So an introduction to this lab. In this lab, we're looking at projectile motion and applying Newton's second law to that motion. And we accomplish this through using tracker, glow script coding, and fundamental physics concepts. And we assume in the beginning that there's no air resistance and no friction. So some fundamentals going into this lab is that we're using Newton's second law. So for projectile motion, this law states that the only force acting on a projectile is gravity, which results in a constant downward acceleration g. So when you looking at equations that we would use for this lab, it would be one F net equals ma, which means that the net force equals mass times acceleration. And then we would use both velocity update, which is final velocity equals initial velocity, plus the net force divided by the mass times change in time. And then position update, which is just final position equals initial position plus the net force times change in time. So when going to the experiment in itself, we used an object, which was a ball of paper, which is approximately 4.5 grams, as stated from Google. And then the surroundings is just air resistance specifically, which is determined through glow scripted tracker. And then the initial conditions, which is specifically the initial position, which is 0.174 meters in the x direction, 0.280 meters in the y direction, and then 0 meters in the z direction. And so for our procedure, we record an object being thrown at a projectile. We then import that object recording into Tracker to find the observed position at specific times. We then create a computational model in GrowScript to find observed position. We then create a spreadsheet with Tracker and computational model and compare the graphs. So for our tracker analysis, as you can see from the graphs, the X position analysis is linear while the Y position graph is parabolic. And then in the next section, when using our computational model for GlowScript, we can see more clearly that in the position X versus time, it's linear, which means specifically that there's no net force acting in the X direction. While in the position Y versus time, this is parabolic because of that net force of gravity. It causes that graph to shift from a linear graph to a parabolic graph, which means that it's increasing the velocity going downwards is increasing as the ball moves down. And then the trajectory of the object also shows this gravitational force acting as the net force. So a discussion that is particularly important is drag force, which states how in tracker analysis, drag force is considered and shown in the data, and the computational models does not include drag force. So what does that mean? That means that the shape of both of the models is generally the same, specifically because while drag force is present, it does not necessarily change the projectile of an object specific entirely. So the shapes of the models are generally the same, but there's differences specifically with like the velocity of the x direction. It's supposed to be constant in a projectile motion, but because of drag force, this can vary. So when looking at potential errors, mostly it would come from glow script and drag tracker errors, which include incorrect calibration, deviation in placing the center of mass, and then a misalignment of the x and y axis and not using an accurate measuring tape to measure the calibration of the object. And then some surrounding forces is just air resistance and drag force and any other opposing forces. And those forces can then make a difference between the glow script and the tracker analysis. And yes. And lastly, for our what if, we asked the question, what if this object was thrown straight up instead of at a projectile? Would it take the same amount of time to reach the ground? The answer is no. The time it takes the object to reach the ground is determined specifically by the vertical component of its velocity. When the object is thrown at an angle, it has a reduced vertical component, which means that it takes less time to reach the ground. But when the object is thrown straight up, it's completely vertical, which means it takes more time for it to reach the ground.